Now let's look at pages 117 to 121, which are the sample problems found in pages 109 to 123. This is a note card of some equations that you're going to want to be familiar with. And what I want you to notice is that all of them relate activation energy, which is E sub A. So notice we have E sub A in all of these. And the rate constant, K. So here's my K, 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 and temperature. And so there's the temperature. And temperature should be in Kelvin in each of these. Temperature, temperature, temperature. R in all of these is going to be the constant 8.314 joules per mole Kelvin. So all of these are really pretty much derivatives of each other. And basically they allow you to determine either activation energy, knowing the rate constant and the temperature, or the temperature, knowing the rate constant and the activation energy, etc. And so you'll want to jot down these equations, pause the video, jot down these equations, and save them for your Moodle quizzes. Now let's look at the top of page 117 at example 14.38. For a certain reaction, B goes to products, sketch the graph of energy versus reaction progress with an activation energy of 100 kilojoules and a delta E of negative 23 kilojoules. So we'll sketch a really rough graph here. Reaction progress is on the x-axis and energy is on the y-axis. So first let's look at our delta E. It's a negative value, which tells us that we have an exothermic reaction. So that means that energy is released, and so the products have less energy than the reactants. So I'll just kind of arbitrarily say, okay, the products, say, are here at 23 kilojoules, and then let's say the reactants are here at 46 kilojoules. So 46 minus 23, I'm sorry, 23 minus 46 would give you a negative 23. So my reactants started out with more energy, so my reactants are here, and my products have less energy after the fact. So there's my rough sketch of where reactants and products are. Now, the activation energy is 100 kilojoules. So from the point of reactants, you should go up by 100 kilojoules, so let's call this 146. And so up here is the top of the hill where the activation energy lies. And so we can connect the rest of this. And so that's a general sketch of this reaction pathway. Obviously not to scale, but it's just asking you to give a general sketch of the graph. So from this point to this point is where our activation energy is, and it equals 100 kilojoules. So consider the reaction B goes to products with an activation energy of 100 kilojoules as above. How much will the reaction rate change if you heat it from 25 degrees Celsius to 35 degrees Celsius? So basically, how much faster is the reaction at 35 degrees compared to 25 degrees? So let's look at our equations that we should have jotted down earlier. And we're given an activation energy and we're given two temperatures. Notice there are two different temperatures. So I'm going to want to use one of these equations, 2, 3, or 4, since they deal in two different temperatures. And we're given the activation energy, and I'm going to go ahead and go with equation number 2, because what I really want to know is what is this ratio, the K2 versus the K1. This would describe the rate change if I knew the K2 versus K1 amount. So that would be the rate of the increase. So we're going to use equation number 2. So here's the equation recopied. Let's take a moment and recognize that R is equal to 8.314 joules per mole Kelvin. We've been given the activation energy in kilojoules, so I'm going to actually go ahead and change that from kilojoules to joules. So 100 kilojoules times 1,000 is just essentially 100 times 10 to the 3 joules. Now we can enter in our information. So this is what I'm solving for. So luckily the equation is already set up to solve for that. Notice that the A's actually cancel out with one another. And so my answer is going to be equal to e to the negative 100 times 10 to the 3 joules divided by 8.314 times the temperature, and we're using temperature 2, so 35 degrees Celsius plus 273 is going to be that temperature. And this is all going to be divided by e to the negative 100 times 10 to the 3 over 8.314 times 25 degrees Celsius plus 273 in order to make it Kelvin. I believe in the solution they use 273.15 if you want to be really specific. So now, how do we solve this? Let's get our calculator. So now to type this in our calculator, we'll hit e to the x, and then we'll type in negative 100 times 10 to the 3 divided by, open parenthesis, 8.314 times, open parenthesis, 35 plus 273.15, close. I'm going to go ahead and hit equals, and this is the answer of the numerator. Then I'm going to hit divided by, and now we'll enter in what's in the denominator, e to the x, negative 100 times 10 to the 3 divided by, open parenthesis, 8.314 times, open parenthesis, 25 plus 273.15, close. And we get a rate change of 3.7, which means that the rate of this reaction is 3.7 times faster when the temperature is increased to 35 degrees from 25. Example 14.40, the rate of reaction B goes to products will increase by a factor of 3.1 when the temperature increases from 25 degrees Celsius to 43 degrees Celsius. Find the energy of activation. Now let's look at our list of equations and see which one's the best suited for this type of problem. We want to find the activation energy, so it's highly recommended that we use this one since it's already set to solve for activation energy. So let's rewrite that equation. So now let's go ahead and plug in our values. The activation energy is going to equal to R, which is 8.314, remember that's joules per mole Kelvin, times the natural log of, and the KH over the KC is the factor of 3.1, and so you would take the natural log of 3.1, and then we're going to multiply times 1 over the colder temperature, which is going to be 25 plus 273.15, and then subtract 1 over the hotter temperature, which is 43 plus 273.15. And all of that is going to be the inverse taken to the negative 1. So we'll start by doing the math in the parentheses here, where I'll take 1 divided by, open parenthesis, 25 plus 273.15, close, minus 1 divided by 43 plus 273.15, close parenthesis. And then I'll hit equals, and now I'm going to take that value to the negative 1, equals, and then I get all of this in parentheses. I'm going to multiply that times the natural log of 3.1, close parenthesis, and times 8.314 equals. We get a value of 49,259. Keep in mind that this is in joules. However, if I wanted to know it in kilojoules, then I would divide by 1,000 joules, because usually activation energy is expressed in kilojoules, and so you would get 49.259 kilojoules per mole. And this is the activation energy for this reaction.